Hey everyone, I'm Anish. Welcome to PrepFusion. So today we'll be starting a new chapter that is basically the frequency domain analysis, right? So up until now, what we have been doing? We have been doing mainly time domain analysis, and after that we did a bit of root locus where we did like the variation of my poles with respect to my sigma plus j omega plane, right? So variation of my OLTF with respect to some parameter. But now, right, what we'll do? We'll do the frequency domain analysis where we'll understand the frequency response of my system, and we'll try to bring out few information from that, right? So in time domain we understood the system performance, how the system performs. Does it perform fast? Does it perform slow? Like how is my peak overshoot, how is my error, steady state error, all those things we understood. So from frequency domain also we can understand few things like the stability, all those things. Like from time domain also we can understand, but with frequency domain also we can understand, right? So let's see, like why do we need to like study this. Like this is also helps in a few other things, right? That's why we study this chapter. So this is the lecture one. So in the lecture one we'll understand the frequency response of a system, right? So like what generally happens is people will teach you like you give some sinusoid input and you get sinusoid output, which is a function of your frequency itself if the system is LTI. But why does that happen? Generally people tend to skip the proof. So obviously I will prove it, but I will give few part homework to you, so that you can figure it out for yourself. So proof will be lengthy, but I have made it shorter so that just the important bits you get to see by me, and if you want to go more deep into that, then you prove it for yourself, right? So like so what is a frequency response? So frequency response basically deals with the response of the system when a sinusoid input is provided, right? So if the input is sinusoid, the response that we get is known as the frequency response. Why? Because sinusoid is basically a function of frequency, right? So like it has some frequency omega. Sorry, as I was telling, is that in time domain, right? We used to give a unit step, right? Unit step. Does it have a frequency domain response? Does it have any frequency component with it? No, right? It doesn't have any frequency component. So like in time domain this doesn't have any frequency component. That's why like we call this one frequency response, as with sinusoid signal it has some frequency component with it, right? So yeah, as like unit step doesn't repeat itself, no, right? It doesn't repeat, it stays constant at let's say one magnitude. But sinusoid, right, the cycle repeats, keeps on repeating, this point is repeating, hence it has some frequency component with it, right? So yeah, that is for like why do we call it a frequency response for a sinusoidal input. That, I hope you got the point. Now, the magnitude and phase relationship between the sinusoidal input and the steady state output of a system is termed as frequency response. So if I give some sinusoid input, right, to a LTI system, I will get my output also as sinusoid. Okay, the frequency will remain same, but the phase and the magnitude will change. And that phase and magnitude relationship is known as the frequency response basically. Why will they change? Why will the frequency remain same? Frequency will remain same as my system is LTI. Why all of this? I will try to prove it to you in the uh, next few slides. Okay? But what do you mean by steady state response? What do you mean by steady state response? So let's take an example here, right? So you have, I hope you have studied the transient response up until now, and there is one chapter which is the AC transient, right? So what happens in AC transient? If you give some sinusoid input, right, you get some sinusoid output, right? But there is some transient, there is some exponential term initially, then obviously it dies down towards the ending stage, but initially, right, it has some transient with it. So yeah, that is basically what do I mean by steady state. So initially my output won't be sinusoidal, right? It will be a combination of exponential and sinusoidal, right? Then at steady state, if the system is stable, then what will happen? That transient, right? The transient will die down, just like the AC transient, right? Just like the AC transient. I hope you have studied that. So AC transient will die down. Only the sinusoid response will remain. So hence, the steady state output is known as the frequency response, because initially it is a combination of both transient and the frequency response itself. So that we don't call it. So we call the steady state output of a system as frequency response. I will try to prove it. There also you will understand, right? So this is my block diagram, right? I hope you understand. This is my block diagram, and I'm giving some sinusoidal input here, and I'm taking some sinusoidal output here. Okay, so like some output here, and this output is known as the frequency response, basically. So let's say considering a linear system, right? Linear and stable system, linear and uh, stable system, right? stable system. Okay, if you consider a linear and stable system, then what will happen? Basically, right, my like if I give some sinusoidal input, the output that I will get is something like this. Steady state output will be something like a sinusoid function itself. So my C of t, right? Let me pick a color. My C of t will be simply magnitude C sine, frequency will be same, omega t plus phi. Now what will be this phi and what will be this C? We just prove it, right? We just prove it. So let's see. Basically too many C's. So let's prove it basically. So proof, right? Proof. So what is my input? My input is this one, right? My input is this one. Okay. My input is this one. So let me name this as like E naught of sine omega t. That will be more easier. So we'll name this one as A naught sine omega t, right? A naught sine omega t. Now, right, what is my this r of like this Laplace transform of this r of t, right? So I want to like solve within Laplace domain. Obviously, that will be much more easier, right? I will simply multiply with transfer function and then I will get my c of s, right? And then I can do the inverse Laplace. So what is my r of s? My r of s is basically e naught of, like, I hope you know the Laplace transform of sinusoid signal, right? So it is E naught of omega by omega square plus A square. So here, sorry, not this one. So this is omega only, S square plus omega square, right? S square plus omega square. So I hope you remember that one. Okay. For cos, it used to be S over here, right? It used to be S over here. So this is my Laplace transform of this R of t signal, right? Now, what is my transfer function? So here, right, what is my transfer function? So my transfer function is basically equals to this g of s upon 1 plus g of s into h of s, right? So this is my transfer function. Okay. So yeah, now I will just copy this one and paste this one here, right? So what will be my c of s basically? So what will be my c of s? My c of s will be simply this r of s into t of s. Now I want to simplify this equation. So what I will do is I will simply write this t of s as a function of n of s by d of s, where n of s is also a function of s and d of s is also a function of s in the numerator and in the denominator. So I can write my t of s equals to n of s by d of s. Okay, just for simplification purpose, and also what we're assuming is like this, right? The poles, all the poles lie on the left hand side of my s plane, right? So this we have to assume, else at the ending stage where we'll get to the conclusion, our proof won't be valid. So obviously this means system is stable, that we know. So all the poles lie on the left hand side of s plane, right? All the poles lie on the left hand side of s. Okay. So yeah, this is what about my transfer function is. Okay. So like obviously we're assuming system is stable. So hence from here we can understand system is stable. So yeah, this is what this is about. So like what I can write this further simplify this R of s and T of s. So like what is T of s? So let me write this one later and let me write this one first. So what is T of s? T of s is n of s by d of s basically. And what is R of s? R of s is a naught w s square plus omega square basically. So omega I can write it as omega naught also, but I'm not writing it because there will be some confusion at the end. So I'm writing this as s square plus omega square. So what can we do? We can do the partial fraction basically, right? We can do the partial fraction. How many roots do we have? Like this will have, let's say, this will have p number of roots, right? So this denominator will come in one section, right? Partial fraction. And here, right, I have two roots, right? S equals to plus j omega and minus j omega, right? So here I will get two terms, okay, due to this one, okay, and due to this I will get, let's say, p terms, p poles, but I'm not writing that I'm just writing it as it is, right? How? Let me show to you. So this c of s, right? C of s, further I can simplify it like this one. So there will be two terms due to this one, okay, due to this one there will be two terms. I'm not messing around with this one, I'm just keeping it as it is. How? I will show you, right? So let's name this as a1 s plus j omega, and then this one as a2 s minus j omega. And what about this one? So I will name this one as, okay, so if you would have studied partial fraction, what you could have done is like taken this one as n dash of s. These are different, right? This n of s and n dash of s is different, okay, and this is d of s only, okay. Obviously I don't know the like how many poles I have, what is there, right? So I will just keep it as it is, okay. D of s I will keep it as it is, and this like the numerator will change, obviously numerator will change obviously because I'm doing the partial fraction, right? So yeah, this is basically the partial fraction of all these things. So now what you can do is to find the frequency response, right? To find the frequency response, like you have to put s equals to j omega, right? S equals to j omega. So here, right, I have to like to find, so not to find the frequency response, to find the coefficients, right? To find the numerators basically, this a1, a2, all these things, right? We have to put like the residue. We have to put this poles here, right? Poles here, and we'll find the residue basically. Okay, so we'll apply the partial fraction. So to find a1, what we have to do? What is my a1 equals to? What is my a1 equals to? Let me just check one thing. Is it fine? What is a1 equals to? So a1, right? a1 will be simply equals to my limit as s tending to minus j omega. Okay, this s plus j omega into t of j omega, right? So this is what my a1 is, okay. This is what my a1 is. So what will happen basically, right? So this is just the residue. I hope you can calculate, right? Or you simply solve it here, okay, you will understand, okay. I'm not going too much deep into this, okay, because we have already done partial fraction so many times, so I'm not going too much deep. So bit of it you have to understand by yourself also, right? So this is what my a1 coefficient will be. So what is my t of j omega? T of j omega is this one, right? uh, sorry, like, sorry, not t of j omega, sorry. This is t of s, right? T of s, okay. So what is my t of s equals to? T of s is equals to this one, right? T of s is equals to this one, and like I don't know the value of this one, so I'll just keep my t of j omega as it is, okay. But like, okay, I am missing one more term, sorry. Like this is r of s into t of s, right? Sorry, r of s into t of s. So what will happen? I will put limit s tending to minus j omega, and this will still be r of j omega. Now what is r of s? I know r of s, I know, right? R of s is this one only, right? So I can write this one So like let me write another line, or else you will not understand basically. Let me C of s. Okay, so this is what my this residue is, right? This is what my residue is. If you multiply by s plus j omega on both sides and put s equals to like this minus j omega, and then all these terms will get vanished and this term will only remain, right? So I hope you're understanding what I'm doing. So yeah, this is what I get, right? Now from here also I have another term, t of minus j omega. Obviously I don't know what t of s is, right? Transfer function could be anything, right? I don't know what the system is, so I'll just simply replace s equals to minus j omega here, right? So now I have s plus j omega here, and there is also hidden s plus j omega here, that will get cancelled, right? So this is basically combination of s plus j omega times s minus j omega. Okay, so s plus j omega will get cancelled. I will be remained with s minus j omega. So limit s tending to minus j omega, s minus that s plus j omega gets cancelled, right? So and here, right, I have t of minus j omega. So now I can put s equals to this minus j omega, right? Here, right, I couldn't have put here because this would have got given me a 0, right? As I got to cancel here, hence I can simply put s equals to minus j omega. That's why I was waiting for this moment, right? So like that, yeah. So now I can put s equals to minus j omega. What I will get is minus e naught j omega by minus 2 j omega t of minus j omega. So this omega will get cancelled, right? Omega will get cancelled. Okay, sorry, this minus I shouldn't write here because you will get again confused. This minus is here only. This minus is here only. Okay, so this minus will get sorry, this omega will get cancelled. What I will be left with this one, right? So my a1 coefficient, okay, I got my a1 coefficient, right? So my a1 coefficient is this is minus, okay, 2j. If I get the j above, it will become plus, but I'm not doing it. There are some reasons, right? So this is omega will get cancelled. This is t of minus j omega. Okay, so this is what my a1 coefficient is equals to. Now let's find out what is my e2 equals to. So what is my e2 equals to? A2, right, again will be similar only. Limit as s tends to this time j omega, right? What you do is multiply with s minus j omega on both sides, right? Multiply with s minus j omega on both sides, and then we put limit as s tends to plus j omega. Then this term will get vanished because like it has s minus j omega, and I'm putting s like s equals j omega. This will get to 0. This term is vanished. This term is also vanished. Only this term and this term are remained, right? So this s minus j omega will get multiplied here also, and I'm doing the limits. Okay, I hope you understood. So limit as s tends to j omega into c of s, right? So this is c of s. So now what we need to do is basically, right, uh, this is now like basically replace c of s with this one, the same procedure, right? Same procedure. So replacing with this one, I'm just copy pasting, not even writing. Okay, sorry for that. uh, okay, yeah, this one is here only, right? And now like you replace r of s, right? Replace r of s with this one, and this is still here, right? Let me get this over here. Okay, okay. So yeah, now what will happen again, right? The same thing, that basically there will be some cancellation here, right? So this s minus j omega and this like s has two components here. So I will be remained with, sorry, like this, right? I will this time replace with plus j omega instead of minus j omega. So this will be plus j omega. And limit, this time I will write extending to j omega like this, right? This will get cancelled and I will be remained with a naught omega. Omega is just a constant value, it's just a frequency of the sinusoid input, right? And this is s plus j omega, right? The other term got cancelled, right? And this is t of j omega. Okay, so this is what we get. Now what is happening? Now I will simply put s equals to j omega. What I will get again, right? That will get cancelled out, and my a2, right? a2 a2 will be equals to basically e naught by 2j into t of j omega. Okay, so my a2 is basically this one, right? a2 is basically this one. It is a naught by 2j into t of j omega. Okay, so now like I have to find some relationship between t of j omega and t of minus j omega. Then I can further simplify this one. Okay, so yeah, let's see, right? So one thing is true, right? The t of minus j omega, the magnitude of t of minus j omega and t of j omega will be same. How? Let's take an example, right? So like I will write here, okay, that like magnitude will be same, but the phase will be different. Phase will be basically negative. Okay, so t of j omega, let's say it has some magnitude, right? Like t of j I can write in polar form. How? It will be magnitude t of j omega. Okay, then what is the other thing? It has basically angle component, right? T of plus j omega. Okay, that we know. Now like we can write it like this one. So or sorry, we can write it like this one also, e raised to power j phi, right? Okay, like the angle form also we can write. Okay, angle form also we can write same volume. Okay, so this is the polar form basically. Now what is my phi angle? Phi, right? What is my phi angle? Phi angle is basically my angle of t of j omega, that whatever I was writing, right? So now one thing to notice here is if I make it negative. Okay, if I make it negative, then what will happen? I have t of j omega magnitude, right? T of j omega magnitude. Okay, that will still be same. That will still be same. Okay, but my phase, right? Phase this time will be t of j minus j phi. Okay, phase this time will change. Okay, why? We'll see. We'll see. Basically, right? The magnitude of t of j omega and t of minus j omega are same. Okay, the magnitude of t of j omega and t of minus j omega are same, but the phase is basically negative, right? Phase is basically negative. So t of j omega minus t of minus j. Okay, so yeah, this is basically what my phase and the relationship between the positive and the negative frequency, right? So how does this happen? Okay, I'll just do one example and there we'll understand like why does this happen. So let's take one example, right? So if I take one example, what do you see? Let's take like I have one p of j omega. Okay, just taking one example, transfer function equals to 1 by j omega into j omega plus 1. Okay, so this is my transfer function basically, right? Now what do I need to do for finding the magnitude? So for finding the magnitude, what do I do? Plus p of j omega, right? If it is plus p of j omega, what is the magnitude? Basically, like generally what we used to do is directly write this omega here, but what is the procedure? The procedure is you have to do like 0 square. What is the real part of this one? It's 0, right? So it is 0 square plus omega square. Then we do the under root, right? So the real part is 0 and the imaginary part is omega itself. Here, right? What is the real part? Real part is 1 and the imaginary part is omega itself. So it is 1 square plus omega square, right? So what I am left with is omega by 1 plus under root, like under root 1 plus omega square. This is what I am left. So yeah, this is what this is. And like now what is the angle of p of j omega? What is the angle of p of j omega? So angle of p of j omega is basically phi 1. Let's name this as phi 1. Now what is the procedure basically? Like how much angle does this one provide? So this is tan inverse 0 by j omega, right? Tan inverse 0 by omega. Sorry, I'm telling you the opposite. It is tan inverse omega by 0. So it is infinity, but it is at the denominator. So if it shifts to the numerator, what happens? I put a negative sign, right? So that's why I get a, okay, I will write this one anyways, minus tan inverse omega by 0. And what does this provide? Again, this one is minus also because this is in the denominator, right? Not in the numerator. So this is minus tan inverse omega by 1. It is y over x, right? Y over x. So what I'm left with, this is tan inverse infinity, which is a 90 itself. So minus 90 and this is tan inverse omega, right? Tan inverse omega. Okay. So yeah, this is what my p of j omega is, right? So what can I write my p of j omega as? My p of j omega equals to magnitude of p of j omega into e raised to power j51, okay, into e raised to power j51. Okay, this is what I can write for the plus j omega. Now let's name this as case A. Now let's go to the case B basically. So what is the case B basically? So in case B, right, what I'm doing, I'm finding the p of minus j omega. So what can I write the p of minus j omega as? So basically replace wherever there is omega, replace with minus omega. So this will become minus j omega into minus j omega plus 1. Okay, so this is what my minus j omega is, right? So where is this? This is in the like fourth quadrant itself, right? So like if I make the quadrant here, right, I just do this in rough. Okay, where are these points? So I hope you know how to find the angles, right? I will not tell you this time. So like the where is this minus j omega located? So basically distance in the real axis is 0 and it is in the negative y direction. So I am at this point, right? And what is the angle with respect to my positive x axis? It is like minus 90. I'm going in the clockwise direction, right? So it is minus 90. Okay, so like due to this the angle contribution is minus 90, and due to this what is the angle contribution, we'll see, right? But first let us find the magnitude, right? First let us find the magnitude. So what is my magnitude? Again, right, if I want to find the magnitude of p of minus j omega, what I will do, I will just simply proceed with the same uh, method, that is g, it has real component 0, right? This component has real component 0 and it has imaginary component of minus omega. But what is the thing here is, as we are squaring, right, as magnitude is always a even function, magnitude is always a even function, right? As we are squaring here, then this becomes positive itself. Okay, and this is also 1 square plus omega square, which is simply equals to 1 by omega into 1 plus omega square. So yeah, this is this one and basically this one, right? So this is familiar to the previous one, right? This one, okay, p of j omega. So minus p of j omega. So like, sorry, not this one, the magnitude is equal, right? Magnitude is equal. Okay, magnitude is equal. Okay, so these are equal basically. But what about the phase angle this time? What is happening to the phase angle? So the phase angle, right? Basically, the phase angle, uh, like angle of p of minus j omega. Let's name this as phi 2, right? Let's name this as phi 2. And what I am seeing is basically it is in this region, right? So due to this, what is the angle contribution? It is basically minus 90. And it is in the denominator, so sign will interchange. So it will become plus 90, right? Plus 90. It will become plus 90 basically. So now, right, this is plus 90. And like what will this one become? So this, right, this is negative y and positive x, right? So it's somewhere around here again, right? It is contributing some negative angle basically. So it is minus tan inverse omega, okay, but as it is in the denominator, it will go in the numerator, hence it will become plus tan inverse omega. So this is plus tan inverse omega. So I'm not going further into this because I've already explained angle very well, right? So you should be able to figure this one out by yourself. So like this is 90 and plus tan inverse omega. So what is this? This is basically negative of this one, right? Negative of this one. So what I can observe is my phi 2, phi 2 is negative of phi 1, okay? So this I can observe. So what is the relationship? Basically my p of g omega, okay, minus g omega will be simply equals to magnitude of p of j omega into e raised to power this minus j5, okay. Okay, because like there it was phi 1 is equals to minus phi 2, right? So I can simply replace with phi 1 equals to phi, so I can replace with minus phi. Okay, so like why am I doing all this hassle, right? This is polar form. I hope you know all this, right? This is polar form. Okay, so I'm not explaining. This is the magnitude and this is the angle basically. Okay, so why am I doing this much of hassle to get to one conclusion, right? So what was my e1 equals to? So e1, right, e1 was equals to this one, okay, e1 was equals to this one. So what I can write my t of minus j omega as, okay. So let me copy this e1 and take this here, and what I can write my t of minus j omega as, right? What I can write my minus t of j omega. So this, right, I can write as like magnitude of plus t of j omega into angle of minus j phi, right? I'm naming this angle as minus j phi, okay. Already proved, right? Already proved in the example. Now what is my e2 equals to? What is my e2 equals to? So my e2, right, 2j into magnitude, this is only simple one, right? Tj omega into e raised to power plus j phi. Now let me replace this in the previous example, right? In the previous equation. So what was my this c of s equals to? This c of s was equals to this one, right? This one. So I will replace my e1 and in e2 here, right? So we'll replace my e1 and e2 here. If I replace my e1 and e2 here, what do I get? So this, right, this one e1 is equals to this one only, right? So we'll copy this one here. So like this, right, this is a constant term, right? This is a constant term, okay. This is a constant term. This does not depend with the basically, what do you say, does not depend with the uh, s, right? This does not this is not a function of s. This is some constant omega, right? Omega is the frequency here. Omega is the frequency, so that's why I was writing omega not, else it would be like bit difficult. So like this is phi, right? Phi is also a function of omega, right? As you can see from here itself. phi is a function of omega here, right? Phi is a function of omega. Okay, so this is constant, right? Frequency omega is a frequency, and this is constant, right? This is not a function of s, not a function of s, right? S is here only. I will write s here. Like I'm replacing simply a1, right? Just replaced a1, nothing else. Okay, so yeah, I think I should write this one as omega naught, else this will be very difficult. Okay, my mistake. So what I will do, I will replace all of this with omega naught, else like you will really get confused, right? Really get confused. Like omega naught is some like fixed frequency. Obviously what in sinusoidal response what we do is we vary the frequency, that's why omega is a variable. But else, like if I don't do this omega naught, right, you'll really get confused. Omega naught is a particular frequency. Okay, so we'll replace everything by omega naught. That is difficult. So I'll just replace everything by omega naught, right? And then I will just come back, right? Okay, I changed everything to like omega naught, right? So omega naught is a particular frequency tone, right? So that you don't get confused, right? So like this is a function of omega naught, right? And like I have been dividing this with s plus g omega naught, and all this, right? All this is a constant. Okay, all of this is a constant. Do keep this in mind. Okay, so or what you can do is like this, a1 is a constant, right? A1 is a constant. What you can do is better, what we should do is directly take the Laplace transform, right? Directly take the Laplace transform. E1 will remain outside. This is a constant. This is not a function of s, not a function of s. Okay, so what is the Laplace transform of s plus a, right? What is the Laplace transform of s plus a? It is e raised to power minus at. But here instead of a I have j omega naught, so it will be e raised to power minus j omega naught t. Okay, so do keep that in mind. So it is e raised to power minus j omega naught t. Okay, now what is this one? This one is again, right? This one is plus e raised to power j omega naught t, right? E raised to power j omega naught t. This one is plus e raised to power j omega naught t. That we see. Right? Now, like I hope you understand. Like simply s plus a and s minus a. So what I will do? What is the Laplace inverse of this one? Very important, right? What is the Laplace inverse of this one? So one thing it will be basically, what will happen is, so basically, right, this will be in some form of exponential and some time response. Okay, like some multiplication by t. So what will happen is, so if I have, let's say, this right, this one, if I have, let's say, s by s plus 1 into s plus 2. Okay, why I'm writing it like this one? Because at the starting itself I assume that my system is stable, so all the roots of this one, right, will lie on the left hand side of the s plane, not even on the imaginary axis. So they will be strictly on the left hand side of my s plane, right? So if they are on the left hand side of the s plane, and if I am getting something like this, what will the term consist, right? So if it is something like s into s plus 1 s plus 2, so it will, right, it will have some, I don't know exactly, it will have some t multiplication, okay, into e raised to power, let's say, minus t and plus t into e raised to power minus 2t. Like I don't know exactly the Laplace transform, but some t multiplication will come with some of the exponential, and the exponential terms will be like this one. Okay, so you do the Laplace inverse and you'll see it for yourself. So like how to check, right? How to check? So basically what you can do is do the Laplace inverse of this one, 1 by s plus 1 into s plus 2, then simply differentiate this, because you simply multiply by s. So if you simply multiply by s in the Laplace domain, then you differentiate in the time domain. I hope you remember the Laplace properties, right? So keep on revising the starting lecture, very important, right? So yeah, that is what you do. So you get something t multiplication in the form and some exponentials, right, of these roots. So what I can write here is overall, right, the Laplace inverse of this one, right? What will be the Laplace inverse of this one? So it will be basically contain two terms, right? Contain two terms. Okay, I will name this one here. Okay, basically it will have some coefficient. Okay, it will have some coefficient. I will name this as CLM. Okay, and this is, let me first write it, then I will explain. This is t raised to power m. Now what is the next term? It is some exponential and the poles of the exponential, right? So let me name this poles as p, and it is p raised to power m itself. So it is p raised to power m itself. Okay, so like there will be some terms like this and this. Okay, so my m will go from 1 to some value, right? And my L will go from 1 to some value, okay? Up until the end, how many amount of roots I have, right? How many amount of poles I have, okay? All this will start here, and my terms, right, will look something like this. Now, like, I hope you recall a bit, right? So, like, if I further simplify this one, right? If I further simplify this one, this will give me the sinusoid basically. So, like, let me replace the A1 and A2, right? So, A1 is this one, okay? Make this smaller, and A2 is this one, okay? A2 is this one, and this is simply plus, and still I have e raised to power plus j omega naught t, right? Geometry, and this is still obviously present. So I hope you understand this term, right? So this is basically, I will explain this term a bit in later few slides. So what is happening right now? So if I combine these exponentials, right? If I combine this exponential, what I will see, right? This will become, I'll just replace this here only. This will become simply, if I take the minus common, right? If I take the minus common, phi plus j omega naught t, and here, right, like exponential are getting multiplied, so the powers will simply get added, right? So this is like class 10 maths. So here, right, again this will become 5 plus j omega naught t, right? 5 plus j omega naught t, okay? So this is 5 plus j omega naught t, right? Now what I am observing, like these, right, these terms are same only, okay? These terms are same only. I have like these term, okay? So it is basically like a sinusoid. So what happens in a sinusoid, right? In sinusoid, if you remember correctly, if I take common the e naught, right? If I take common the e naught, so it is also, if I take common this one, so I will take common this one. So I will copy this one, okay? Reduce the size of this one. Now what I will do is, basically I will take this one as common, right? I will take e naught into t of j omega common, okay? So if I take this one common, then what will happen? Okay, I will take this one here, okay? This one I will keep it down in the bottom. Okay, this is minus, and this I will delete, right? I have already taken e naught into t of j omega as common, right? We'll take this one here, and I'll keep this one here, right? So is this looking something familiar to you? So if I just simply make this in one denominator, right? 2j is same, like denominator is same for both of them. So if I make it a single denominator itself, so what can I observe here? I can observe that this is plus actually. I can observe this is e raised to power plus jt minus e raised to power minus jt. So what is this form basically? This form is of sinusoid, right? This form is of sinusoid. Okay. So basically, what do I get? Uh, basically, right. So this, right? If I equate this one, this one I will get as a naught into t of j omega naught, right? T of j omega naught into sine. Now this term, right, this is the sine term, basically the angle, whatever this angle is basically. So I hope you know understand how to break down sine, right, in terms of exponential, that we know. So I'm just converting this, right. So like uh, what is sine omega naught, sine omega t, right? Sine omega t you can write as e raised to power j omega minus e raised to power minus j omega by 2j. Okay, this is how you can write a sine term as, okay, so in terms of exponential. So basically that is what I basically did here, right? So yeah, how is this happening? So you understand, right? It's a few lectures ago I wrote the this exponential form in terms of sine and cosine. So if we break this down further, right, so this is cos omega plus j sine omega, right? J sine omega, so this e raised to power plus j omega, and this is minus of cos omega, like this is minus sine j minus j sine omega, but as I have a minus sign here also, so this becomes plus j sine omega. Okay, so this gets cancelled and I have 2j sine omega, and I have in the denominator 2j gets cancelled, and I am remained with sine omega only. So I hope you understand, right, how I'm getting this term like sine omega. So like maybe there may be some confusion. So this is sine omega only. So this becomes like whatever is inside this one, right, this comes here, right? So this is basically, okay, sorry, one thing I forgot to write here. Okay, here I had a j also, sorry. Okay, I had a j also, sorry. So here, right, I forgot to write the j here itself. I know you were screaming, where is the j, sir, where is the j? J is here only, don't worry, it will come. Okay, this is j. So what I will do, I will take the j also common here, right? So what I will do is take the j common. Okay, okay, take the j common here, right? So like again, right, whatever is inside this j term, right, it will come here. So it is basically uh, omega naught t plus phi. Now what is this phi? Phi is basically function of frequency itself, this omega naught itself, right, the angle that we found out. Okay, I hope you understand. So this is sine j omega naught t plus phi. Okay, so as you were seeing, right, this a naught is same, right, a naught and this omega naught is same, everything is same, but this, like, it is getting multiplied by some t of j omega naught and omega t, but I'm forgetting I have this also, right? So this I will write, okay, copy and paste over here. Okay, so my c of t, okay, I just took the Laplace transform of this one. So from here, right, I just took the Laplace transform just like that. Okay, not here, okay, here, took the Laplace transform, right? Okay, I hope you got the crux of this one. So like what I was telling is basically if you take the Laplace transform of this one, you get this. Okay, then you further simplify and you get this. Okay, so what is basically this part? This part is the sinusoid response part, right? This part is the frequency response basically. Okay, this part is the frequency response, and this part is the, what is this part? This part is basically the AC transient, right? AC transient. Okay, this part is the AC transient basically. So this is what we get. So like this is my c of t. Okay, this is my time domain response if I give some sinusoid input. But sir, you told we get a sinusoid output. Where is the sinusoid? Sinusoid is here, but I also have a transient, right? So that's why I told you, right, I have to assume that my system is stable. If my system is stable, this exponential, right, the power of this will always be negative, right? Always be some minus t, minus 2t of so- some of that sort of form. Okay, if my exponential is negative, right, if my exponential is negative, then at t equals to infinity, what will happen? At steady state, what will happen? So let's go for the steady state. So C of steady state equals to limit st tending to infinity, hence c of t, right? So what will happen here? Basically, like this, right? If I make it t tends to infinity, can I define a value for this one? No, right? This is always oscillatory. Can I define a fixed value for this one? So for t tends to infinity, let's say t tends to 1000, then t tends to 2000. Can I fix this value? No. This is question mark, right? So this I will write as it is, right? So this I will write as it is. Okay. Now this one, right? What is happened to this one? Now, as my system is stable, all the poles are on the left hand side, as explained earlier. This exponential will always have a negative term, and as my t increases, this will reduce, right? E raised to the minus t, let's say. So as t tends to infinity, it goes to 0, right? So this, right? This will go to 0. Okay. Why? As like obviously I assume system is stable and all the poles lie on the right hand side of a spline. Okay. Sorry, not right. Sorry, on the left hand side. On the left hand side of the spline, right? Okay. So yeah, that's why this goes to 0 as my t tends to infinity. That's why I told you, right? At steady state, okay, at steady state, I will only get this sinusoid, right? And this transient part, right? AC transient part will die down, okay, at steady state. So like as opposed to my unit step response, my response here will be oscillatory. Okay. Why? Because my input, right? My input itself is oscillatory. It is not stable, right? Sinusoid. It is oscillatory, right? Input is oscillatory. So obviously, even though my system is stable, but as my input is oscillatory, my output would also be oscillatory, right? But if my system was unstable, this term, right, exponential term, the exponential power would have been positive. Let's say e raised to a plus t, right? Then at t equals to infinity, what is happening? It is going up. Okay, it is going up. Hence, this will not die down. This will be present over there. So yeah, that is an issue. That is an issue, right? So if I had like stable system, I have e raised to a minus t. This will die down. Die down. Okay, go to a 0, and I will be remain with only this one. Okay, so yeah, that is what this is basically. So I have written down few key points, right? As opposed to unit step response, the steady state sinusoidal response will be oscillatory in nature. Okay, as already explained, right? It will be oscillatory because my input is also oscillatory, right? Input itself is oscillatory, so this will be oscillatory. Now, like, why do we do the frequency response? As I told earlier, right, we do the time response also, but we judge the performance of the system from time response, right? How the system performs, okay, various parameters. But why is frequency response important? So when we want to analyze noise, right, noise in the system, it is much easier to analyze in the frequency domain rather in the time domain. That's why we take the help of frequency domain itself, right? So yeah, there also frequency domain is very important. So in communication systems also, mainly we give sinusoidal input, right? So there also this frequency domain is important. So obviously whatever we are studying, right, we will implement this in like in real life and in other subjects like communication systems, all those things. So yeah, this frequency response is also very important. Okay, so basically, right, like this is the key point, the response will settle down to a sinusoid of same frequency. Like we got to know, like as the system is LTI, it will settle down to sinusoid of same frequency. So I should write this as LTI system, right? LTI system is LTI, hence this will happen. Okay, but obviously there will be some scaling in magnitude and it will be shifted by phase phi here, right? As we can see, there is some scaling in magnitude. A naught is scaled with magnitude t of j omega naught and some shifted by some phase phi. Okay, phi and t of j omega naught obviously are function of frequency itself, right? The input frequency itself. Okay, and this is the what the system does. System shift the sinusoid frequency by some phi angle and it's multiplied by some t of j omega naught, right? So yeah, that is what this one does. Okay, so yeah, now, right, now, like this is the property of a stability system. So the frequency response that I'm getting, like this property, right, is like this is the property of a stability system. So this is basically the continuation of this point I wrote over here also, the property of a LTI system. So like now, right, I told you, like I gave you one steady state output, right, y of steady state, and it is a function of frequency itself. Okay, but how can I, like what is the use case of this one? I told you few use cases, right, to understand the noise, to like analyze in communication systems. But in control systems, what we'll do is to find the stability of the closed loop system using the frequency response of my OLTF, right? So that's why we are studying OLTF. Okay, so but how can we visualize with respect to omega? Like why we need to visualize? First we need to understand why. First we need to understand why. How I will, that is coming in the next slide, but why is it coming over here? So basically, right, why is it coming over here? Basically to to find stability of CLTF by frequency response OLTF, right? By frequency response OLTF. Okay, so like this is the motivation behind this. Okay, why we want to visualize the variation of steady state output with respect to frequency. Okay, so like how will we vary? Basically what we'll do is we'll vary the system itself. So why, like, because like why we will vary the system itself, like system transfer function itself. So basically, right, my y steady state, okay, my y steady state, or I let me write as c steady state, is what is it related with? It is related with my t of j omega naught, right? T of j, or you can say t of j omega. Okay, with different omegas I will get different responses. Okay, my steady state will also be different, right, for different omega. Now this t of j omega obviously varies with omega itself, right? It is a function of omega itself. So that's why I want to do it this one. So if I find the variation of t of j omega with respect to omega, right, then what I will observe is I can find the steady state output for any omega naught, right? For any omega naught. If I can find the response for this one, right? Find the response, like plot t of j omega with respect to omega, right? Then I can find my steady state output for any omega naught, right? Because my output is simply a scaled version of the input amplitude and shifted by phi, which is a function of omega naught itself, or you can say which is a function of t omega naught itself. Okay, t j omega naught itself, right? So yeah, that is what we'll do. We'll simply plot these two, right? Okay, but let's say I don't know t of j omega. I don't know t of j omega. Okay, I don't know t of j omega. I know OLTF, right? I know OLTF. Okay, this is the CLTF, and I don't know t of j omega. Obviously this one also will do, this one also will do. Okay, at later stage, but initially now we'll do different things. So but still without t of j omega, still I want to understand the stability, right? At least I won't be able to find my steady state output. Okay, that I won't be able to find, but can I say that yes, it will be stable or it will be unstable without the t of j omega? So that is the main thing. Okay, that is the main thing. So without the t of j omega, can we see, can you see this one, right? Obviously that we will study in the next few lectures. So like what are the different plots, right? What are the different plots? So this, right, this is a polar plot. Okay, this is the polar plot, which is basically the plot of the real of, okay, this one I should write as OLT, right, not t of j omega. Simply I should write this as OLT. Okay, so this is a bit wrong because generally what we do is we'll generally plot the OLT. Okay, so yeah, this is difficult. What I will do is simply write, like I will copy this one. Okay, and what I will do is reduce the size actually. Generally we plot the OLT basically, not the this one. Okay. And this one is basically, this is the OLTF, right? We do the OLTF. Not T of G omega, because T of G omega is a closed loop transfer function, okay? So that you don't get confused. So this one, right? I will actually basically copy this one and paste this one here. Okay. Like, what is the difference between Nyquist and polar? So like Nyquist also uses some different things, right? Like the Nyquist contour and all those things. Also like mapping theorem that we will obviously study. Don't worry. So basically, right? Polar plot is the plot of real of my OLTF, real part of my OLTF versus the imaginary part of my OLTF, right? With a variation of frequency, frequency is varying from 0 to infinity. How? We'll understand in the next lecture if you don't understand. I just giving you the brief overview and definition. And what is my Nyquist plot? Nyquist plot is also the same, but it uses different principles also. Okay, that also we will understand when we will study the Nyquist plot chapter. So first we will study the polar plot, right? But here, right, what is the main important difference? My omega is varying from minus infinity to plus infinity. So omega contains all the real values, right? Also, we have another plot which is the Bode plot, right? Which is the Bode plot. So in Bode plot, right? Bode plot also we plot the OLT itself, okay? Bode plot also we plot the OLT itself, not the transfer function. You can plot the transfer function obviously, but the transfer function is for another chapter, that is the frequency response of second order systems. So in Bode plot, right? So obviously we'll study all these things. Don't worry if you don't understand anything, because I haven't explained anything, right? So I'm just giving you a brief overview of what will come in the chapter basically of the frequency response. This is a long thing. Okay, we won't take too much long, but this is obviously few things we have to study, right? So Bode plot has two things, right? One is the phase plot and another is the magnitude plot. So obviously when we will study, we'll understand a bit more, but for now just understand that what things we have, right? And what things you have to keep in mind. So we start with polar plot. Okay, start with polar plot. That is in the next lecture we'll start with polar plot, and we'll understand what is the polar plot and all those things, right? So like I hope you got the basic crux in this lecture. So what was the main aim for like doing this lecture? Basically to understand what is frequency response. What is frequency response? Frequency response is a steady state response when we give some sinusoidal input to the LTI system, right? So deals with the response of the system when a sinusoid input is given. Okay, so like now we got to know that there is a magnitude and phase relationship between the sinusoid input and the steady state output. Okay, steady state output, it is steady state. Okay, obviously it is related with the input frequency, right? Input frequency, and obviously there is the amplitude is scaled and the angle is added. Okay, all those things have happened, right? All those things have happened. Okay, this is my transfer function. Then like I told you that we'll get output something like this. The frequency, right? Frequency won't change. I prove to you, okay, how the frequency isn't changing. So like I hope you understand, as my poles are lying on the left hand side, then right, like this one will be like this form, right? Okay, just try out few examples, right? Try out few examples and you will see we'll get form like this one. I'm not proving this one. So that was that this is what I was telling in the start of the lecture, right? So I will not prove everything, right? So as it will take too much time. Okay, so like you were just getting the brief idea, right? Brief idea that yeah, I will get the form something like this one. Okay, then what I will do, I will simply like put t equals to infinity to find the steady state output. But as this is oscillatory in nature, right? So I won't be able to tell what is the steady state value of this one. This will always oscillate, right? Okay, won't be able to tell. But for this one, right, as my poles are lying on the left hand side or in the RC circuit also, AC transient, you got to know that this will die down, right? After some time, this will die down. Only my sinusoid input will be remained. So that RC circuit is also LTI system. Okay, so it is a linear system, right? And it is also time invariant. So yeah, so there this dies down and this is remaining, and exactly that is what I did. This is dying down and this is remaining. Okay, so system is stable, that's why. So here I got to know the form. I proved to you why the form that we get is like this one. Okay, so yeah, then we done understood few points. And then like what is the motivation for doing this, right? What is the motivation for doing all this frequency response and all those things? So like you might say, how can I find the stability of CLT by using the frequency response of OLTF. That we'll understand. Without even writing the CLTF, we can find the response, like the stability of CLTF without even writing the CLTF itself. With help of only OLTF we can find. So why is this beneficial? All those things we'll study later. Okay. So for now, like there are three plots, right? Mainly we'll study three plots. One is a polar plot, which is the plot between the real of OLTF and the imaginary of the OLTF, right? So where omega varies from 0 to infinity. And this is a plot of real of OLTF and the imaginary of OLTF, where omega varies from minus infinity to plus infinity. And also we'll study the Bode plot, where I have two sections, right? One is a magnitude plot, where I plot the magnitude versus omega, and another is a phase plot, where I plot the phase versus omega, right? So phase of OLTF, magnitude of OLTF. So keep that in mind. OLTF, right? OLTF. Obviously, you can plot for any transfer function, doesn't matter. But here in control system, we'll try to plot the OLTF, and through the OLTF, we'll try to find the stability parameters, right, of the CLTF, all of the system itself. Okay. So yeah, that is it for this first lecture. I hope you understood everything, right? If you have any more doubts, you can put it down in the comments or ask in the Telegram group, right? So for now, this is it, and I will see you in the next lecture.